Okay, our next part that we're going to talk about is Newton's laws of motion, particularly Newton's first law of motion, because that's really where statics comes into play. So Newton's laws of motion directly relates to statics. Okay, so in terms of what we're examining, Newton's first law states that if the resultant force acting on a particle is zero, the particle will remain at rest if it's originally at rest, or will move with a constant speed in a straight line if it's originally in motion. Now, the key to this is constant speed. That means no acceleration. So we can see that a particle in equilibrium is either going to be at rest or moving in a straight line with a constant speed. Those are the only two options we have. So if a particle doesn't behave in either of these ways, it's not in equilibrium, and our resultant should not equal zero. So like in that last problem we had, where we had a resultant equaling to something at a certain angle, okay, that is not in equilibrium. That is, those forces together are going to cause some motion at that bolt, okay, in that specific direction. So most of statics does involve using Newton's first law to analyze an equilibrium situation. Okay, so a large number of statics problems can be reduced to problems concerning the equilibrium of a particle. Okay, and through this we draw a free body diagram, or an FBD is just part of a method of choosing a significant particle and drawing a separate diagram showing this particle and all the forces acting on it. So just like in the previous problem that we looked at, right, in example 2.3, all those forces intersected at one point. Okay, so that is concurrent coplanar, right? All of them are on the same plane, and they are concurrent because they go through the same point. Okay, so just some tips. If an object is in equilibrium with two forces acting on it, and you know the forces must be equal in magnitude but opposite in sense. If the object is in equilibrium with three forces acting on it, a good tool to use is a force triangle, and we will actually be doing an example of that. Okay, so a force triangle is just the three forces acting on the object. They're drawn tip to tail to form a closed triangle. And we can either use the law of sines or law of cosines to find things out about the rest of the triangle. If the object is in equilibrium with three force or more forces acting on it, you may want to use the equilibrium equations and break up each of the forces into its x and y parts, or its components. This will only work if you have two unknowns. Okay, so that means if I know F1 equals 150 newtons, and I know the angle it's acting at, I can put it into its x and y parts. So the most common types of problems are going to be two unknowns represent the two components of a single force. That means F is broken up into F sub x and F sub y. The magnitudes of two forces, and we know their directions, or we determine the maximum or minimum value of the magnitude of a force. Okay, those are our three most common types of problems that we are going to be dealing with. Okay, so let's take a look at example 2.4. Okay, and for this problem, we have a ship in an unloading operation. A 3,500-pound automobile is supported by a cable. A worker ties a rope to the cable at A and pulls on it in order to center the automobile over its intended position on the dock. At the moment illustrated, the automobile is stationary. The angle between the cable and the vertical is 2 degrees, and the angle between the rope and the horizontal is 30 degrees. What are the tensions in the rope and the cable? Okay, so this is a problem of equilibrium under three coplanar forces. Okay, we've got three forces going on. So we're going to treat point A as the particle and we're going to solve the problem using a force triangle. So what we have, okay, is we have the tension of the rope between A and B. I'm just going to draw this at a larger angle. Okay, so if I take a vertical line, dotted line, this is actually a really small angle. It's only 2 degrees. Okay, and we don't know what this is yet. T, A, B. Okay, then we have the weight of the car. Well, that's pretty easy. That's going straight down, and that is 3,500 pounds. Okay, our third force then is from the tension that the guy is pulling with to help keep it in alignment, the car in alignment, right, to where it wants to go. Okay, so we will call this T, A, C, and this, probably should have written that on the other side. That is going to be at 30 degrees. Okay, that's our free body diagram. So if we want to take this and draw a force triangle, okay, we have to draw all 3 of these forces tip to tail. You can start with any force that you want. You don't have to start with one in particular. Okay, for me, I usually start with the weight. I don't know why, it's just my habit. So I'm going to start with that first. So I'm going to draw my weight going down like this. Okay, and then what I'm going to do is I'm going to draw that TAC vector. Going off this way. Okay, and then TAB, so this is TAC. So TAB is going to go from here all the way back up to here. So notice I have all of my vectors drawn tip to tail. Okay, so this is TAB. Okay, this vector we know is 3,500 pounds. Okay, so I want to know what these two are. But in order to do that, I'm going to need some angles. Okay, so I'm going to go back to my free body diagram here for a sec, and I notice that this is 30 degrees, right? So TAC is 30 degrees, so this is where it's at right here, right? So if I went where these met and I draw a dotted line, this angle here is going to be 30 degrees. Okay, so that means 30 plus 90 is going to be an angle that I need. So 30 plus 90 is 120. So I'm going to just erase that dotted line here. Okay, and I'm going to put 120 degrees in here. Okay. So I still am probably going to need another angle because right now I can actually figure out what TAB is. Okay, but it would be a heck of a lot easier if I knew one of these other angles. And this one is going to be the best one to use because then it's opposite of TAC and I can use the law of sines. So TAB, I know at the bottom that this here, this is 2 degrees right here. So I have another parallel line right here, right? So if you remember from geometry, if you have a line like this, 2 parallel lines, and a line that's going across them like our TAB is, right? This angle, we'll call it theta, is equal to that angle. Those 2 angles are equal. So if this is 2 degrees, this one right here also is going to be 2 degrees. Okay, and then if we wanted to know this other angle, we can easily do that because the sum of three angles in a triangle always have to be 180. So we're going to have 180 minus 120 minus another 2 is going to be 58. So if we really wanted to know that, we could. 58 degrees. Okay, so what I'm going to do is I'm going to use the law of sines to figure out what TAB and what TAC are. Okay, so the law of sines, what we want to do is let's do TAB. So I'm going to take TAB over the sine of its opposite angle. Okay, so that means the opposite angle from this side is 120. Okay, TAB touches this angle and this angle, so I know it can't be opposite. So that means the sine of 120 degrees is equal to, okay, so then I've got this 3,500 pounds. Okay, so that's going to be my other side, 3,500 pounds for my horrible writing on this. Okay, and I'm going to take that and divide it by the sine of its opposite angle. Okay, so 3,500 pounds touches this angle and this angle, meaning this one has to be my opposite. So that is going to be the sine of 58 degrees. Okay, so all I'm going to do is solve for that. Really, and all I have to do is take this 3,500, divide it by the sine of 58 degrees, and then multiply by the sine of 120. And I'm going to get, for TAB, okay, I'm going to get a value of 3,570 pounds. Okay, so I'm going to use the same force triangle here, and I'm going to find TAC. Okay, so I'm going to start with TAC since that's what I'm trying to solve for. So let's do TAC over the sine of its opposite angle. TAC, sine of its opposite angle, if we're not sure. Let's see, it touches that angle and that angle, so it's got to be the sine of 2. Is going to equal, and I can just use the same one if I want to, the 3,500 pounds over the sine of 58. So let's just do that. So 3,500 pounds divided by the sine of 58 degrees, and I'm going to get a value for TAC. Okay, and that's going to be 144 pounds of tension. Okay, and I'm going to ask myself, do those numbers make sense? Well, I would definitely say that 144 pounds probably makes a heck of a lot of sense for that rope, right? Because he's pulling on this rope. So that's definitely what I would at least expect. I wouldn't expect it to be this large. If I got that number for that person pulling on that rope, I would say I probably did something wrong. Okay, so this is an example of where we can use that force triangle. I've got 3 forces and they all have to be in equilibrium, meaning if I draw a force triangle, draw them in a triangle shape, that I should be able to find the other 2 forces that are acting on it. Okay, we will continue on the next little video.